Dear learners, so welcome you all in this video. Here we'll start the new broad area in the basic electrical engineering, that is AC fundamentals. So alternating current fundamental. So here we'll see in details about the sinusoidal voltage and currents, their mathematical and graphical representation, then concept of cycles, period, frequency, instantaneous value, peak value, then average value, RMS value, peak factor, form factor, phasor representation of AC quantities, phase difference, lagging, leading and in phase quantities, rectangular and polar representation of the phasor. So let us start the topic in detail. So this is what the graphical representation of sinusoidal waveform. So why it is we say it is a sinusoidal waveform? So because it is a sine of the angle theta, right? So that's why it is called sinusoidal waveform. We change that angle theta, and with respect to that we plot the magnitude, and this magnitude comes like the curve, the positive half cycle it contains and the negative half cycle, so completing it a complete cycle. So this is called the sinusoidal waveform. If you see the equation of it, it is V is equal to Vm sine theta. So how we plot is, suppose this is the E or V, that is current or voltage. We are plotting this magnitude with respect to the angle. And the equation we have, V is equal to Vm sine theta. So what we have, if we put the value of theta is 0, then sine 0 is what? 0. So this complete term E or I, that is voltage or current, will get 0. If we put the value of this theta is 90 degree, then what? Sine 90 is 1. So that means sine 90 is 1. So this term gets neglected. So V is equal to Vm. That is, V is having the maximum value. So this is what the maximum value at pi by 2. That is 90 degree. When we put the pi, that is 180 degree. So again we have 0. So V is equal to 0. So here it comes again at 0 on the axis. When we put 3 pi by 2, that is 270 degree, again it will have negative maximum. At that time it will have minus sign, so we'll get the negative maximum value. And when we put 260 degree, that is 2 pi, again we'll get the 0 value. And in between that we can put any angle, so we'll get the respective values over this waveform. So that's why it is called a sinusoidal waveform. So we can plot this waveform with respect to this equation. This is the sinusoidal waveform equation, right? So this is the graphical representation in terms of the waveform. Now mathematically the sinusoidal quantities can be represented in various ways, right? So with respect to the maximum value on angle theta, so we have V is equal to Vm sine theta. V is the instantaneous value, Vm is the maximum value, and sine of the angle theta. In terms of maximum value and angular velocity, it will be Vm sine omega t, angular velocity. In terms of maximum value and frequency, Vm sine 2 pi ft, where f is the frequency, t be the time. In terms of maximum value and time period, that is 2 pi by t. So when we put f is equal to 1 by t, that is frequency is reciprocal of time period. So f is equal to 1 by t, when we put, so 2 pi by t. And this is what for the maximum value and time period. So in these various ways we can write in mathematical form for this sinusoidal waveform. Now how this waveform is generated? So for understanding how this waveform can be generated, we have simple singleton generator, singleton alternator we can also say. So this is we consider to understand how the sinusoidal waveform can be generated. So singleton generator, so there are two conductor A and conductor B, and the conductor A is connected to the slip ring and conductor B is connected to, conductor A is here and the B is here. And this slip ring, over the slip ring the brushes are continuously sliding and the two connections are brought out to connect the external load. So this is how the structure of this singleton generator, and there is a permanent magnet N and S pole. Okay, so we can say this singleton as an armature and this NS as a field poles. So it will produce the magnetic field, and inside this magnetic field the conductor is moving. So this is the condition that the current carrying conductor placed in magnetic field, it experiences a force. This is how the Faraday's law we can apply here. Not the current carrying conductor, we have to apply the Faraday's law. This conductor is moving inside the magnetic field, so there will be a induced EMF in the conductor, right? And this is due to the dynamically induced EMF, right? The EMF will be induced due to the dynamic principle. Now let us see the different position of this conductor, and then we can see the waveform. So here, suppose this is the position A and the angle is 0 degree. So this is exactly parallel to the axis of the magnetic field, right? So at this position, suppose this is the position, reference position, and the angle by which the conductor is making is 0. So we have there will be no induced EMF in the conductor. Now let us say this conductor is moved by 90 degree in anti-clockwise position. So the EMF will start inducing, and at 90 degree it will have maximum value. So continuously this conductor is moving now exactly opposite to the first position, that is moving 180 degree. So we will have again at 0 position because it is again parallel to the axis of magnetic field. So continuously moving 270 degree, we will have negative maximum, and at original position we will have 0. So this is how at different position we are getting the magnitude of the waveform, right? So this is what the principle of dynamically induced EMF. When this conductor is placed in the magnetic field, the EMF will get induced in that conductor. This is according to Faraday's law. This is the waveform generated from this principle. So sinusoidal waveform, there are different parameters we have written here. The maximum value, the negative maximum value, positive upcycle, negative upcycle, 0 to 180 degree, 180 to 360 degree, that is pi, 2 pi, time period t, right? And with respect to time. Okay, now we will define various terms for this waveform: cycles, period, frequency, peak value, instantaneous value, average value, and RMS value. Let us see one by one. So what is cycle? Every alternating wave consists of a repetition of similar part of wave. One such a repetition is called a cycle. See, there will be a repetition of the part which is called the cycle. This one complete cycle contains positive upcycle and a negative upcycle, consisting of one complete cycle. So we can say one full cycle or the time period, which is one cycle is equal to 2 pi radians, 180 degree, that is. Time period, it is defined as the time taken by alternating quantity to complete one cycle. So for completing that one cycle, what is the time required, which is called the time period? Very simple, denoted by t and measured in second. Frequency, which is defined as the number of cycles of alternating quantity per second. Number of cycles per second. For 1 second, how many cycles are there? So that is called the frequency. So number of cycles per second, which is called the frequency, denoted by f and measured in hertz. So frequency is equal to 1 by time period, that is inverse of the time, right? So if it is a 50 Hz frequency, so time period will come 0.02, that is 1 by 50, 0.02 second. Then the peak value or amplitude, it is the maximum, positive maximum value of alternating quantity. This is what the positive maximum value from the 0 point to the maximum value. So this is called the peak value or maximum value. Then instantaneous value, it is the value on the waveform at particular instant. So at any instant, what is the value of the magnitude? It is called instantaneous value. Next is the angular velocity. It is the rate of change of angle omega t with respect to time. Rate of change of angle with respect to time. So omega is equal to d phi by d theta by dt, where d theta is the change in angle in time dt as per this definition. If we consider dt is equal to 2, that is time period for one cycle, then the corresponding change in theta is 2 pi. So if you consider for one cycle, then time period is t and the change in the angle is 2 pi. So d theta is 2 pi and dt is t. So we can put it here. So omega is equal to 2 pi by t. And if we put 1 by t, which is the inverse of time period, that is the frequency, then we have omega is equal to 2 pi f radians. So this is the angular velocity for the waveform, for the sinusoidal waveform, right? The next, these are the definitions we are looking. The next part that we'll consider in the next video. So keep watching this. Thank you.